Okay, now we want to talk about the divergence and the curl of a vector field. Before I start, let's make sure we understand about the Dell Operator. Here's your Dell Operator. We used it to calculate gradients some time ago, and it's been used otherwise. And it's a real important operator, as we're going to see. Not so much today as when we really get into the details of what these fields do and what they mean. Okay, now a diverging field, here's an example, f of xy equals xi plus yj. This field diverges from the origin, okay? And you can see the field is always directed away from the origin because the vector xi plus yj is parallel to a vector from 0 to the point xi plus yj, and you're probably familiar with that. If not, convince yourself that it's so. It also gets bigger the further you go from the origin, so we have a field that looks something like this. So that's just an example of a diverging field. Another example of a diverging field would be one that goes inward, like a gravitational field. Since everybody I'm talking to in this class at least has been through physics and understands gravitational fields, also electromagnetic fields. The difference between this field and the gravitational field, other than that the gravitational field of a mass at the origin would point inward, is that the gravitational field doesn't get bigger as you move away from the origin. Okay, the gravitational field falls off as the inverse, falls off in a proportion to the inverse square. Falls off inversely as the square of the distance from the origin. So to get a model of a gravitational field, you would divide this by the cube of the distance to the point xy, because the numerator has a magnitude that is the distance, and you want an inverse square with distance, so you have to divide by the square of the distance, but you also have to divide by the distance to correct for the fact that this expression has a magnitude equal to the distance. So, details aside, you would have an x squared plus y squared to the 3/2 power, the cube of the square root of x squared plus y squared in the denominator, and that would give you a model of a gravitational field, and that's a diverging field. It has a negative divergence, diverges toward the origin instead of away from the origin, so it's not really diverging in the everyday sense of the word, but we still regard that as a divergence. The source of the field in this case will be at the origin. And more about that later. The divergence of F would then be del, divergence is defined, we haven't defined it, it's del dot F. For this field, it's very clear that this divergence would be 2. Now there's no z component specified here. We could specify one. We could do a zk, in which case the divergence would become 3. You would have a field in 3 dimensions diverging from the origin. Can't sketch it in 3 dimensions with any kind of, anyhow, you understand about the 3 dimensions. Now, another possibility is a field that doesn't diverge from the origin, but circulates around the origin. And of course the divergence doesn't have to be from the origin, circulation doesn't have to be around the origin, divergence could be from any point. So just to riff a little bit on that, if I have a mass here, then I'd have a diverging field toward that mass. If I got another mass out here, I'd have a diverging field toward that mass. And then I'd have to combine the 2 diverging fields to get the total field of a function that represents the gravitational field of the 2 masses. Okay, in any case, okay. In this case, a circulating field is one where if you do a path around the origin, and I've done a circular path here, the field tends to run perpendicular to the radial line. Or at least there's a component of the field that runs perpendicular to the radial line. And there's no reason you couldn't superimpose a field that circulates with a field that diverges. Okay, and then that field would not be a pure diverging field, it would not be a pure circulating field. All these vectors, if they represent this function, which is an example of a function that circulates around the origin, and I forget what the beginning of my sentence was. In any case, yeah, if this represents this field, then all these vectors should have the same magnitude. And of course, the magnitude increases as you go out from the origin, so the circulation becomes faster and faster as you move out from the origin, or at least the circulation vectors get bigger and bigger. You'd have the whole space, in this case, just circulating around the origin with a constant angular velocity. If you, and my current class is all familiar with what that means. Okay, so there's a circulating field. The curl of a field is del cross G. So for example, the curl of this field is the constant 2K. Now that is related to the fact that you have a constant angular velocity throughout space, since this is constant. And I'm saying that off the top of my head. Test it, make sure it's true. I haven't gone through the steps of proving it, it just occurred to me to say it. So that's a conjecture. Okay, you can work on that conjecture if you want to. Okay, anyhow, this is how you calculate the curl. It's just a cross product. And for this field, the cross product is easily calculated just using the distributive law. The I component dots with only the j component to give you anything besides 0, and the partial is 1. And the j component dots with the I component to give you something non-zero. And yeah, j cross I is negative k, so you'd have minus the y derivative of this is 1. The y derivative of negative y is minus 1. But that's times the negative k vector. You get the 2k, so that's easy to work out if you understand just the cross products of the I, j, and k vectors with one another. So here's your general definition for any vector field f, not just this field, any vector field f. Divergence is del dot f, and that's a scalar. You do a del dot f, you get just a number in this case. The curl of f gives you a vector. It's a vector field, and we put a little arrow over the curl of the word curl. And that is, we do that when we remember to do that, which I didn't here. Okay? Now there's this important theorem that we can easily prove right here, that the divergence of the curl of f is 0. Okay. And that's because it turns out that the curl of any vector field is a circulating field, or a static field, as would be this case here, because you take the curl of something as a pure circulating field, you just get a constant number. And that's a conjecture. I haven't proved that in my head, but I'm pretty sure that's right. Okay, so to prove this, very simple, we just write it out. We make up some set of symbols for f. Well, pi plus qj plus rk is perfectly good. And we do the curl. We cross this. We do the del cross this field. And then we dot that with the Dell operator to get the divergence. Well, now here I used the distributive law to do my cross product because it was really easy to do that, and why go to the trouble to write out a determinant for something that easy? You'd be more likely to confuse yourself, although that's your choice. But here, since we have full sets of components and all that stuff, it's easy to write out the determinant definition, or the determinant version of the curl. and then we do the determinant, and I'm not going to do that for you. I mean, it's this, partial of r with respect to y minus partial of z with respect to partial of q with respect to z, etc., etc. There it is. And we dot that with the Dell operator. And I had to write that Dell operator small. Originally I just had the Dell there, but I decided I wanted it to do this next step. So then partial with respect to I means partial with respect to x times I dotted with all this is going to give you, well, just the x derivative of this, which is ryx minus qzx. Similarly, the y derivative of y derivative times j, the y derivative operator times the j vector is going to multiply by this, or dot with this, giving you the y derivatives of these things, which are here. And similarly, you're going to get the z derivatives of these, and that's all very straightforward. And then you pair these up, orange with orange, plus with minus. Remembering, of course, that the order of your partial differentiation, your two partial differentiations, the order of the partial differentiations doesn't matter. Okay. Then in the blue, we've circled the two pzy and negative pyz, and similarly that's blue, and then in purple, the q's. It all adds up to 0. Every one of these cancels out, adds up to 0. Well, we just proved that the divergence of the curl is 0. A pure circulating field doesn't diverge. Now I say a couple things about source-free fields, but I'm not going to talk about that right now. We'll take up that topic because I'm not even sure that what I wrote down there is accurate, and I don't want to take the time to think through it right now.